My name is Jackie Johnson, and I'm a Principal Analytical Training Consultant in Global Academic Programs at SAS. I'm going to be talking to you today about our SAS Studio application, and in particular, how to use SAS Studio point-and-click tasks to automatically generate SAS programming code. Here is a brief biography of me. I have been a SAS user since 1999 and have taught SAS in commercial and academic settings since 2009. SAS Studio is our newest interactive development environment for SAS software. You can use SAS Studio for data processing, creating graphs, as well as running all of your favorite statistical analyses and models. SAS Studio provides a visual interface for writing and executing SAS programming code. Today we are specifically going to discuss SAS Studio tasks, which provide a no-code way to run analyses. SAS Studio tasks allow you to specify options through a point-and-click interface, then the task will automatically generate appropriate SAS code for you. Today we are going to access SAS Studio through our environment SAS On Demand for Academics. SAS On Demand for Academics is free SAS software in the cloud for faculty, students, and independent learners. It provides the full functionality of SAS statistical and data science software. And since it's in the cloud, you can access On Demand for Academics whenever and wherever you want to use it. One great feature of SAS On Demand for Academics for teaching and learning is that it is easy to access and easy to set up. You do not need to perform any complicated software installation or compatibility updates in order to use SAS On Demand for Academics. This means you can get started quickly with teaching or learning new analytics skills. Register for SAS On Demand for Academics at welcome.oda.sas.com. We're going to start with two demonstrations. First, we will show how to log in to SAS On Demand for Academics. Then we will take a tour of the SAS Studio interface. We are at the login page for SAS On Demand for Academics. The first thing that you will need in order to log in is a SAS profile. If you do not have a SAS profile, click on the link at the bottom for Don't Have a SAS Profile. This will take you to a web page where you can create a SAS profile. Once you have a SAS profile, enter your login and your password on this login page, then accept the terms and conditions. Next, click the Sign In button. If this is your first time logging into SAS On Demand for Academics, you will be shown an additional window that asks you to choose your nearest home region. After you have chosen your region, you will receive an email that your SAS On Demand for Academics account has been set up. This email normally arrives in 5 to 10 minutes. Once you have received the email, come back to this page, welcome.oda.sas.com, and log in again with your SAS profile. I have already registered for SAS On Demand for Academics, so I'm going to sign in. So I click the Sign In button. When you sign in, you are taken to your dashboard. There are three tabs at the top that we're going to talk about. The first tab is the Applications tab, and you'll notice that this gives us access to the SAS Studio application here. So this is the tab that we're going to use to launch SAS Studio. On the right is the Courses tab. The Courses tab allows faculty, students, and independent learners the ability to create a course in order to share the files with others. Then the Enrollments tab allows all users to join courses that have been created by others. I will click on the SAS Studio icon here to launch SAS Studio software. Now that we have logged in to SAS On Demand for Academics and we've launched SAS Studio software, let's take a look at the SAS Studio interface. On the left, we have a window that has four areas, and we call them risers. The first one is Server Files and Folders. This is where you're going to access all the files that are available to you on SAS On Demand for Academics. If this is not expanded, go ahead and expand all of the folders here. This file system is part of a cloud file system. You do have the ability to upload files from your personal computer as well as download files to your personal computer, but you don't have direct access to your personal computer here. We're going to be talking a lot about tasks and utilities in this course, which is the second riser. I'll expand tasks. This provides several menus that show all different kinds of point-and-click tasks that we can use to create graphs or statistical analyses. The next riser is the Snippets riser. I'll expand the Snippets menu here. This is a place where you can put any code that you find that you reuse very frequently. So for example, there are some pre-written snippets here. In the data menu, we have a snippet for how to import an Excel file or import a CSV file. The last riser is for libraries. And we're going to create a library in just a minute. In SAS, a library is a pointer to a folder that holds SAS datasets. And a library allows us to reference datasets in our code or in our tasks without having to supply a full path to them. One helpful library is the SAS Help library. This is a library that gives you access to several pre-supplied datasets that you can use for analyses. Let's go back to server files and folders. What I want to do now is I want to create a folder that will contain the dataset that we're going to use for this demonstration. I'm going to highlight Files Home, and then I'm going to right-click and select New, and then Folder. And I'll call this folder Demo, and hit Save. Now the demo folder is created, and now I need to upload a dataset that we're going to use for this demonstration. Make sure the demo folder is highlighted, and then I'm going to click on the up arrow, which is the Upload button. This brings up a window where I can choose the file to upload. So I'll say Choose Files. And this gives me access to my personal computer. So this folder that we're looking at is on my personal computer. And I'm going to upload a dataset called Birth. And I'll click the Upload button. We're going to talk a little bit more about this dataset in just a minute. But for now, we've uploaded the dataset that we're going to use for this demonstration. I want to do a couple more things in order to customize our SAS Studio session here. I'm going to go up to this icon with the 3 horizontal lines, and I'll select Preferences. This is an area where you can select different display preferences for SAS On Demand for Academics. In the first one, in General, I'm going to select Size Grid Columns to Content, and that's a checkbox. I'll go to the Startup menu, and on the Startup menu, this tells us the default timeout interval. SAS Studio is cloud software, so it will time out after the timeout interval has elapsed. I'm going to increase this timeout interval to 3 hours, and I think that is the maximum here. I also will go to the Results section here. We're going to see that when we start using SAS Studio tasks, that all of the output can be sent to various types of result files, things like HTML or Microsoft Word or PDF files. So I want to enable PDF files and RTF files to be generated. So I'm going to select those 2 checkboxes. All right, I think that is all the preferences that I need, and I'm going to hit the Save button. Let's get into our analysis of the births dataset. The first thing we want to do is we want to look at some tasks to explore the births dataset. The first task we're going to use is the Characterize Data task. What this task is going to do is it's going to generate some basic descriptive statistics for continuous variables, and it will give us frequency tables for categorical variables. It's also going to provide histograms for continuous variables. The dataset that we're going to use in this demonstration is the low birth weight dataset. The outcome in this dataset is the birth weight of the baby. This is in grams. A baby is characterized as low birth weight if their birth weight is 2,500 grams or less. We have some additional continuous predictors that we can relate to the baby's birth weight, and this is age of the mother in years and weight of the mother at her last menstrual period, so you can think of that as her pre-pregnancy weight. We also have some categorical predictors. We have ethnicity, we have smoking status during pregnancy, yes or no. We have history of premature labor, and that's the number of premature labors. We have history of hypertension, yes or no. We have presence of what is called uterine irritability, yes or no. And then finally, we have the number of physician visits during the first trimester, which can be 0, 1, or 2. So we're going to go to SAS On Demand for Academic Software now and take a look at the birth dataset. I'm going to open up my Tasks menu here. And the task that I want to open up is in the Data menu. And we'll go to Characterize Data. I'll click on the 4 arrows in order to maximize my screen, and this gets rid of the left menu. Now the first thing that I need to do is I need to specify a data set. And remember that I told you that in SAS, data sets, they're stored in what are called libraries, and a library is a pointer to a folder that contains a SAS data set. So what I want to do before I start working on this task is I want to create a library for the folder that contains the birth data set. I will go back to my server files and folders, and I'll highlight the demo folder, since that is the folder that contains the birth data set. I will right-click and select Create, and then Library. You can choose whatever name for the library you'd like, but I will select the library name Demo, and I will select the checkbox for Recreate this library at startup, so that when I exit out of SAS and come back in, this library reference will still be available to me. And I'll say OK. One way that we can check that this library has been created is we go to our Libraries riser, expand My Libraries, and now I can expand this demo library. And we see that the birth dataset is in our demo library. Let's go back to our Characterize Data task. I need to specify the birth dataset, so I will select the dataset using this square icon. I will click on the demo library and select the birth dataset and hit OK. The Characterize Data task has the ability to try to choose the best analysis for your type of variable. So you could put variables in this automatic characterization, and SAS will try to figure out what kind of variable it is. We're going to go ahead and tell SAS which variables are continuous and which are categorical. I'll put the continuous variables in the automatic characterization section. I click the plus sign. I want to add the age of the mother. I'll hold down the Control key to select other variables, and this BWT is the birth weight, and then also LWT is the mother's pre-pregnancy weight. And I'll hit OK. I'll expand Custom Categorization, and now I want to add categorical variables. I click on the plus sign. I'll select the variable low, which is our outcome for low birth weight or not. I'll hold down the Shift key in order to select an entire range of variables. So I'm holding down the Shift key, then I'll select the last variable, FTV, and then hit OK. This task has options. I'm going to unselect Frequency Chart, so that for our categorical variables, we display frequency tables only. Notice on the right that SAS code has been generated. So by choosing the options in this point-and-click task, we have generated appropriate SAS analysis code. I'm going to hit the running man to run this code. By default, we are in this split viewer display here. I'm going to change the display to the code results display, and that puts the results in one screen. I'm additionally also going to open these results in an HTML file. So that gives us just a little bit more space in order to look at these results. Let's look first at the frequency tables for the categorical variables. Notice that at the top of each of these tables is a label describing the variable that we're summarizing. On the left is the actual variable name. So here the variable low is a variable that describes whether or not the baby's birth weight was less than 2,500 grams. So it equals 1 if the birth weight was less than 2,500 grams, and equals 0 if not. We have ethnicity, which takes 3 categories, smoking status, which takes 2 categories, history of premature labor, which is takes two categories, yes or no. History of hypertension, which is also a yes or no categorical variable. We notice, for example, that we don't have a lot of mothers in this data set that have a history of hypertension. We also have a fairly small percentage of mothers that had a history of premature labor. We see the variable history of uterine irritability, and then finally the variable FTV, which is the number of physician visits during the first trimester. The reason that we look at these tables is just to get an idea of the different possible levels for these categorical variables. Now let's move on to descriptive statistics for the continuous variables. We have three variables here. The first one is the mother's age. We see that it takes a minimum of 14 and a maximum of 45 years, with a mean of about 23 years old. And notice we have 189 observations in this data set. We also see the mother's weight at her last menstrual period, her pre-pregnancy weight, and that's in pounds. So the mothers were anywhere from 80 to 250 pounds. And then finally, we have the baby's birth weight in grams. And that's a minimum of about 709 grams up to almost 5,000 grams. There are 453 grams in a pound. So the babies in this data set are anywhere from about 1.5 pounds in weight to 11 pounds in weight. Now we can look at some histograms of these continuous variables, and we're looking at these just to get an idea of the range of values. Here we see the histogram for age. We see a mother out here at the age 45, but otherwise it looks like most of the other mothers are in their 30s or younger. The next graph is the distribution of the mother's weight, her pre-pregnancy weight. And then finally, we have a histogram for our outcome, which is the baby's birth weight. One thing that we might like to add to each of these histograms are some curves. For example, one of the assumptions that we would make if we're using baby's body weight as an outcome is that it is normally distributed. So we'd like to add a normal distribution curve to each of these histograms, and we'd like to add an estimated distribution curve. So that's the distribution of the data. So we look to see if our task is able to do that for us. So I go back to my settings, and I don't have any options here in order to add those curves. So what I'm going to do is I'm going to edit the code that has already been generated. So I go to my code results tab, and I go to the code tab specifically. And you see the code that has been generated here. Now I'm going to click on Edit. This opens the code into a new program window. The code that creates the histograms is from ProcUnivariate here at the bottom. So what I need to do is I need to add some options in this ProcUnivariate code in order to generate the curves on those histograms. So I put my cursor on the histogram statement, and I'll put a slash because that's telling SAS that I want to add an option, and then I'll put a space. And you'll notice that when I press the space bar, we have some options that come up. And so this is showing the interactive syntax that SAS will provide to you if you're not familiar with the syntax of the procedure that you're coding. So here, this is giving me all the possible options that I could specify on the histogram statement. The first option that I want to specify is the normal option, which will superimpose a normal curve. So I select that, and you see that when I select it, some information about that option comes up in the right. So this gives me more description about the option. And if I didn't know that that was the option that I wanted to use, then I could click through several of these and read this information on the right. So I'm going to double click on normal, press the space bar again, and then the second option that I want to specify is the kernel option. And once again, we can read about the kernel option if we'd like. I'm going to double click the kernel option. So now I have completed my code edits, and I'm going to rerun the code. This time I will put the output into a Microsoft Word file. My Word file has opened. I'll scroll down in the file to the section with the histograms. I'll zoom in to make the graph bigger. This is the distribution of the variable age. This blue curve, this is a curve for the normal distribution, and then this red dashed curve, this is a curve for the distribution of the data. At this point, we are really just eyeballing these curves. We want them to be roughly equivalent, and they are. Our data look roughly mound-shaped, roughly symmetric. Let's look at the next graph. This is the distribution of the mother's prepregnancy weight. Once again, the blue curve is the normal distribution. The red curve is the distribution of the data. We see some deviation from normality here. That's just something for us to be aware of. We have a lot of weights of the mother towards the lower end and far fewer in this upper right tail. Then this last graph, this is a graph of the baby's birth weight. So this is going to be our outcome, and this is the variable whose distribution we are most concerned about. Once again, the blue curve is a normal distribution, and the red curve is the estimated distribution for these data. We see that the red curve shows a very symmetric distribution. Our peak isn't quite as high as the normal distribution, but for the most part, this looks roughly mound-shaped, roughly symmetric. So looks like a good distribution in terms of normality. We have just done some data exploration on the births data set. Now we want to start to perform some statistical hypothesis tests. In particular, we're going to perform what's called a two-sample test. So this is a test that's going to be appropriate when you have some continuous outcome and you want to compare the mean of that continuous outcome for a variable that has two groups. So for example, we could ask the question, is there a difference in cholesterol levels between males and females? The type of test that we're going to perform here is called a t-test, and we're going to use the t-test task in order to perform this test. Another related test that we can perform is called an analysis of variance, or ANOVA. And this is very similar to the t-test, except in an analysis of variance, we now have a predictor that has more than two levels. So our outcome is still continuous, but our predictor has more than two levels. An appropriate question here might be, is there a difference in cholesterol levels for individuals with different causes of death? And so you can imagine that there can be many causes of death, certainly more than two causes of death. For an analysis of variance, we are going to use the one-way ANOVA task. Let's go to SAS On Demand for Academics, and we'll show how to fit a t-test as well as an analysis of variance on the births dataset. I'm back where we left off in SAS On Demand for Academics. I'm going to click on the four arrows in order to get the left menu back. I'll go to my Tasks and Utilities riser, and now I want to use the t-test task. That is in the Statistics menu. So I open up the Statistics menu and double-click on the t-tests task. Once again, I'll maximize my screen by selecting the icon with the four arrows. I have to specify the data set here. Now, since I used the birth data set in the previous task, it's already been pre-supplied here. But if you do not see the demo.birth dataset specified here, then you want to select the dataset using the table icon. You'll notice on the right that no code has been generated. You'll also notice that there is a red icon with an exclamation point. This is telling me that I have not supplied all the necessary inputs for this task. The first thing I need to specify is I need to specify that I want to do a two-sample t-test. So I will change this from one sample t-test to two-sample t-test. What we want to do here with the births data set is we want to see if the mean baby's birth weight is different for different levels of some of our categorical predictors. My analysis variable here is going to be the birth weight. And I'll select OK. And then my grouping variable, I only select one. And we could select any of these grouping variables. I'm going to try smoking status. And I'll select OK. You'll notice that the red exclamation point is gone, and now code has been generated in the right window. I'll go to my Options tab. I'm going to uncheck Tests for Normality. Whenever I change any of the options, the code changes over here on the right. I think those are all the changes I want to make, and I will hit the Running Man to run the code. I'll go to the Code Results window, and this time I'll look at the results in an HTML file. We have fit a 2-sample t-test here. And so what we want to do is we want to compare the mean birth weight for mothers that did and did not smoke during pregnancy. This top table provides us the mean birth weight in each of those groups. So it looks like the mean birth weight among mothers that smoked was 2,773 grams. The mean birth weight among mothers that did not smoke was 3,055 grams. We also have the standard deviation of that mean. Under that, SAS has computed the difference in birth weight between these two groups. So the difference is 282 grams. We want to know if the mean birth weight in these two groups is statistically different. So we need to look at some of the other tables in this output. One of the assumptions that is made in a t-test is that the variability of the outcome is the same in both groups. So we go to the bottom of this output, which is a test for equality of variances, and we see that this number, a p-value, is large. In particular, it's greater than 0.05. So this means that we don't have any evidence that the variability of birth weight is different in the two groups. That means that we can look at the results for a test that assumes the same variance in birth weight in both groups. Next, we look at the table above, and we look at the line that's labeled pooled. What this shows here is it shows us the test statistic for a t-test, which is 2.63. It compares that test statistic to a t-distribution with 187 degrees of freedom. That is a statistical probability distribution. And it computes a p-value of 0.0092. This p-value is really small, so this tells us that, in fact, the mean birth weight is different comparing mothers who did and did not smoke. Let's go back to SAS On Demand for Academics, and now we also want to fit the one-way analysis of variance. I'll minimize my screen, go back to my Tasks menu. Now I want to open up the Linear Models menu, and I want to double-click on one-way analysis of variance. And I'll maximize my view again. Once again, the demo.birth dataset has been pre-supplied here, so I don't need to change it, but you should change it if you don't see that here. The dependent variable, this is our outcome variable. So this will be the variable birth weight. And then the categorical predictor, we want to choose a predictor that has more than 2 levels. So one predictor that we could use is FTV, which is the number of physician visits. And you'll notice that code has been generated in the right. I want to look at my Options tab to see if there are any options I want to change. I'm going to uncheck Welch's variance weighted ANOVA. Everything else looks pretty good. So I will run this code using the Running Man. I'll go to my code results window, and this time I'll put the output in a PDF file. And let me zoom in. So this is my PDF file. It's opened in the browser. This is showing the results of the GLM procedure in SAS. What we're interested in knowing is we want to know if the mean birth weight is different for the different levels of FTV, which is number of physician visits during the first trimester. Since we have only one variable in this model, we can inspect this top table. This top table presents us with a test statistic that we compare to the F statistical probability distribution. That test statistic is 1.79. The degrees of freedom for that test statistic are 2 in the numerator and 186 in the denominator. And when we compare that test statistic to the F distribution, we get a p-value of 0.17, which is not particularly small. So this tells us that we don't have evidence that the birth weight is different for different levels of number of physician visits during the first trimester. But let's look at some of the rest of this output to try to understand why this might not be an interesting relationship. Here we have a box plot. On the y-axis is the baby's birth weight in grams, and on the horizontal or x-axis is the number of visits to the doctor in the first trimester. And we see that the mothers had either 0, 1, or 2 visits to the doctor during their first trimester. The diamond here, this is the mean. So that's the mean birth weight within each of this number of visits. And then the horizontal line is the median. And then the box itself shows the first and third quartiles of birth weight. We see that these boxes, if we look at where they hit vertically, we see that the boxes are pretty similar, right? The diamonds, the means are pretty similar. Also the horizontal line, the median, is pretty similar. Looking at this graph, it's not that much of a surprise that there was not a significant relationship between birth weight and number of physician visits during the first trimester. Previously, we did some data exploration with the birth data set. We generated descriptive statistics for continuous predictors, as well as our outcome, and then we also generated some frequency tables for categorical predictors. Next, we did some basic hypothesis tests. We looked at how to compute mean of baby's birth weight for a 2-level predictor using a t-test, and then we also compared the mean birth weight for a 3-level predictor, which was the number of physician visits during the first trimester. Now what we'd like to do is we'd like to fit a formal statistical model for the baby's birth weight. And before we do that, we're going to do some additional data exploration. And in particular, we want to answer a few different questions. So the first question that we're going to ask is, are there relationships between baby's birth weight and each of the continuous predictors? So specifically, do we see a relationship between birth weight and the mother's age? Is that relationship positive or negative? And how strong is that relationship? How can we quantify the strength of that relationship? We're going to perform an additional exploratory data analysis. And in this exploratory data analysis, we're going to focus on creating several graphs. In particular, we will create a matrix of scatter plots that graph each of the continuous variables in our data set versus each other, and we'll also produce some regression scatter plots. We're going to use the data exploration task in order to create these scatter plots. The second task that we're going to look into is the correlation analysis task. The correlation analysis task is going to allow us to quantify the strength of the relationship between each of the continuous predictors. Let's go to SAS On Demand for Academics, and we'll learn how to use these two tasks. I am back in SAS On Demand for Academics, and now I want to open up the data exploration task. I'll go into the statistics menu in my tasks and utilities riser and open up data exploration. Once again, I'll select the maximize button so that the task window takes up our entire screen. As always, make sure that the birth dataset is specified as the analysis dataset here. This data exploration is going to focus first on the relationship between continuous variables in the dataset. So I will specify the 3 continuous variables that we have. That's the age of the mother. I'll hold down the control key in order to select multiple variables, the birth weight of the baby, and then also the mother's pre-pregnancy weight. And I'll click OK. Let's go to the Plots tab. We want to keep scatterplot matrix checked. I'm also going to add some regression scatter plots. And the response variable on these scatter plots will be the baby's birth weight. Everything else looks good. And now I'll hit the Run button. I'll go to my Code and Results tab, and I'll put these plots into a web page. Here we see a scatter plot matrix, and this is showing plots of each of the continuous variables. First, we see a plot of mother's age versus mother's pre-pregnancy weight. This shows a general positive relationship, showing that as we increase in the mother's age, the mother's weight also increases. On the right, we see a graph of the mother's pre-pregnancy weight versus birth weight. As expected, we also see a positive relationship here, in that the mothers that weighed more before they became pregnant also gave birth to heavier babies. Finally, in this bottom left, we see a graph of mother's age versus birth weight. Now, we don't have any regression lines on this plot, so it's kind of hard to see the relationship here. And I'd say there's not really a relationship between age and birth weight. But what we're going to do next is we're going to create some regression scatter plots. And that will allow us to put a plot of mother's age versus birth weight, and also a plot of mother's pre-pregnancy weight versus birth weight, and each of these will be in its own graph. So let's look at that next. So here's birth weight on the y-axis, and we've graphed it versus mother's age. And superimposed on here is a regression line. This was the graph that we saw in the bottom left on the scatter plot matrix. And here, now that we have an actual regression line and this plot is bigger, we see that there is a slight positive relationship between mother's age and the birth weight of the baby. So the older mothers, in general, gave birth to heavier babies. Let's look at our second regression scatter plot here. On the y-axis, again, we have birth weight. On the x-axis, we have the mother's pre-pregnancy weight. And here we see this relationship just a bit more clearly than we saw in the scatter plot matrix. We see that mothers that were heavier before they became pregnant also gave birth to heavier babies. We can also look at birth weight for different levels of the categorical predictors. So let's use the data exploration task to do that now. Let's go back into the settings for our data exploration task, and I'll go to the Data tab. I'm going to remove age and also the mother's pre-pregnancy weight from the continuous variables. And I'm doing that by pressing the trash can to remove that column. Now what I'm going to do is I'm going to add some categorical predictors. This will allow us to show baby's birth weight for each level of the categorical predictor. Now you'll notice that in light gray here, we see that only 2 variables are allowed here. Sometimes throughout these tasks, there's a limit on the number of variables that you specify. We have more than 2 categorical predictors of interest, so we're going to look at these in groups of 2. I click on the plus sign, and I'll start with number of doctor's visits in the first trimester, and I'll hold down the control key, and then I'll also look at presence of uterine irritability, and hit OK. I'll go back to my plots option, and I'm going to check comparative box plot here. So this will give me a graph in order to compare the birth weight for each level of these predictors. And I'll hit the Running Man again. And I'll go back to my Code Results tab. Once again, I will open this output into a web page. Here's a box plot of birth weight by levels of history of uterine irritability. I'll make this a little bit bigger. We do see a slight relationship here. It's not clear whether this is a statistically significant relationship, but this left box, this is the birth weight for mothers that did not have a history of uterine irritability. The right box, this is the birth weight for mothers that did have a history of uterine irritability. And we see that in general, the birth weight is higher for mothers without history of uterine irritability. Let's look at the second box plot. So this is the distribution of birth weight for each of the different levels of number of doctor's visits. And we saw this before in a previous graph. Let's change our 2 variables. We'll go back into the settings and go into Data. And I'll remove each of these classification variables and add additional categorical predictors. So here, this is history of hypertension and history of preterm labor. And I'll click OK. And once again, run these results. And I'll go to my Code Results tab and open this into a web browser. Here we're looking at a box plot of birth weight for mothers that did not have a history of premature labor on the left, and mothers that did have a history of premature labor on the right. And it looks like mothers that did not have a history of premature labor did tend to have heavier babies than mothers who did have a history of premature labor. Like with the previous variable, it's not clear whether this is a statistically significant relationship, but we can evaluate that later in a linear regression task. Now we see a box plot for birth weight on the y-axis versus history of hypertension on the x-axis. Once again, we see that mothers without a history of hypertension, it looks like overall they gave birth to heavier babies than mothers with a history of hypertension. The width of this box for mothers with history of hypertension, though, is very wide, so this relationship is unlikely to be statistically significant. Let's go back into our task, and we'll look at the relationship between birth weight and the final two categorical variables. So I'll go into my settings, remove these two variables, and I'll add in smoking status of the mother. I'll hold down the control key and also add ethnicity. And say OK. And I'll run the code. I'll go to my Code Results tab, and I'll open these results in a browser. Here we're looking at the mean birth weight for different levels of ethnicity, and the mean is shown by the diamond. It doesn't look like there's much difference in the average birth weight for different levels of ethnicity. At the bottom, this is showing us the relationship between birth weight and smoking status. The mean birth weight for mothers that did not smoke does look a bit higher than the mean birth weight for mothers that did smoke. And remember that earlier, when we ran that t-test task, we did see a statistically significant difference here in average birth weight by level of smoking status. We have used the data exploration task to look at the relationship between birth weight and continuous predictors, as well as birth weight and categorical predictors. Let's return to the graph that we created to look at the relationship between birth weight and the continuous predictors. When we looked at the relationship between birth weight and continuous predictors, we created these two regression scatter plots. So here we see the relationship between birth weight and mother's age, and then we also see the relationship between birth weight and the mother's pre-pregnancy weight. When we looked at these graphs, we commented that they both showed a positive relationship between birth weight and the predictor. And now what we want to do is we want to quantify the strength of that relationship, and we're going to use the correlation task to do that. So let's go back into our list of tasks. I'm going to go into the statistics menu, and I'm going to select the correlation analysis task. What we need to do here is we need to specify our outcome variable, which is birth weight. So I'm going to put that in the second box here. I'm going to put that in the correlate with box. So I'll select birth weight and select OK. And then I want to correlate that with our two other continuous predictors. So that will be mother's age, and I'll hold down the control key and also her pre-pregnancy weight. And select OK. Let's take a look at our Options tab. I'll expand methods. That looks pretty good. For statistics, I'm going to select Selected Statistics. This looks good, so I won't make any changes here. I just wanted to check what statistics are going to be shown. And we'll leave off the plots at this time. So let's go ahead and run this. And I'll put this in my code results viewer. So what we've computed here is we have computed correlation statistics, quantifying the relationship between birth weight and mother's age and her pre-pregnancy weight. We see that the correlation between birth weight and age is about 0.09, and then the correlation between birth weight and mother's pre-pregnancy weight is about 0.186. So we see that the correlation between birth weight and mother's pre-pregnancy weight is stronger because the correlation statistic is higher than the correlation between birth weight and age. And then the second row, these are p-values for a hypothesis test, testing whether these correlation statistics are different from 0. Since this p-value for the test for the correlation between birth weight and pre-pregnancy weight, since this is less than 0.05, we see that this is a significant correlation in that it is significantly different from 0. And since the p-value for the relationship between birth weight and age is greater than 0.05, we see that this is not a statistically significant relationship. When we're trying to interpret the strength of the correlation here, the interpretation of these numbers is going to vary by your field. So for some fields, a correlation of 0.18 might be reasonably good. For other fields, it might not be very good at all. Let's return to the list of questions that we have about the birth dataset. We've done an exploratory data analysis looking at graphical relationships between different predictors and the baby's birth weight, and now we want to formalize those relationships using a linear regression model. One of the questions that we could ask in a linear regression model, for example, is can we explain how a difference in mother's age might impact birth weight? Or similarly, can we explain how a difference in mother's pre-pregnancy weight might impact birth weight? The task that we're going to use is the linear regression task. And so let's go to SAS On Demand for Academics, and we'll fit a linear regression. Let's open up a linear regression task. We're going to go into the Linear Models menu in our Tasks and Utilities menu, and then select Linear Regression. And I'll maximize my screen to get rid of the left side menu. Our dependent variable will be the birth weight. And I'll say OK. And then we have to specify the various predictors in this model. For classification variables, I'm going to go ahead and throw in all the different classification variables that we have. So I'll select ethnicity. I'll hold down the control key. We have smoking status, history of preterm labor, history of hypertension, uterine irritability, and I think that is everything. And I will select OK. It's asking us for a parameterization of effects. I'm going to just leave this at the default. For continuous variables, we will add in age and the mother's pre-pregnancy weight and say OK. And I've realized that I've forgotten one of the classification variables, and that's the number of doctor's visits in the first trimester, and that's the variable FTV. Now you'll notice here that our menu of possible variables to add here is very short, and that's because you can only use each variable in one of these windows, and so SAS is showing only those variables that are left. And so I'll hit OK. This is looking pretty good here. Now you'll notice that no code has been generated in the right, and that is because this linear regression task is unique in that I have further specifications about the model that I still need to perform before SAS can fit this. So I'll go to the Model tab, and this is where I need to enter the model effects. So I'll click on Edit. I'll select the age variable, hold down the Shift key. This selects all the variables, and I'll just add the single effects. So what I'm doing here is I am adding main effects for each of these predictors. I'm not adding any interaction terms, and certainly you could add interaction terms if you believe that there was a reason to do so. So let's go down to the bottom and I'll click OK. And now we see that code has been generated. Let's go to our Options tab. I'm going to turn off some of the diagnostic plots. I think the rest of this looks okay. You'll notice that there are several more tabs for this particular task. I'll go to the Selection task. There is a pull down for Selection method. What this can do is this can use various automated model selection techniques in order to choose the best set of predictors for this model. I'm going to go ahead and select one of these methods, and I will select backwards elimination. So what this is going to do is this is going to start with a model that has all the predictors that we have specified. Then it will remove predictors one by one, starting with the least significant predictor of the outcome. And I will leave all the defaults in terms of the criterion that are being used in order to select the effects. And I'll go ahead and run the code. I'll go to my Code Results tab, and once again, look at this in a web page. Our objective here is to fit a model to explain the variability in our outcome, the baby's birth weight. And we did some backward selection in order to come up with the best set of predictors to explain the baby's birth weight. These first tables at the top just tell us some information about the model. It tells us how many observations are in the data set, which is 189. It tells us the different levels of the variables that we've treated as categorical. So we see those 6 listed here. Altogether, we have 9 predictors. This table is showing us a summary of the backward selection technique. In the first step, the variable number of doctor's visits in the first trimester was removed. Then the mother's age was removed. And then the history of preterm labor was removed. We have some graphs that show fit statistics as we remove these different predictors. I'm going to skip over these for right now, and I want to show you the parameter estimates for the final model that we fit. This table at the bottom characterizes the numeric relationship between each of the predictors and our outcome of baby's birth weight. So we see that the mother's pre-pregnancy weight is in the model. So for every 1 pound increase in the mother's pre-pregnancy weight, that leads to a 4.24 grams increase in the baby's weight. We have various predictors for the different levels of ethnicity. Remember that there are 3 possible levels of ethnicity, and so SAS has given us parameter estimates for the first 2. We also have the predictor for smoking status, then history of hypertension, and history of uterine irritability. Each of these categorical predictors is being shown using what is called a reference cell coding. This is to say that one of the levels of each of these predictors has been set to be what is called a reference cell. So these parameter estimates, what they measure is they measure the change in the baby's birth weight, comparing that level to the reference cell. So for example, for smoking status, babies that were born to a mother who did not smoke on average had birth weights of 354.9 ounces higher than babies that were born to a mother that did smoke. To conclude this output, we have a nice graph showing the observed baby's birth weight, that's the birth weight in the data set, versus the birth weight predicted by the model. In summary, we see that several of the variables that we looked at as predictors do have a significant relationship with the baby's birth weight. And this model, what it's doing is it's looking at those predictors as a group in terms of how much of the variability of birth weight they predict together. So far in this demonstration, we have focused on the continuous birth weight outcome. So this is baby's birth weight in grams. We haven't said much about the other outcome variable that we had in the data set, and this is the categorical outcome, which is equal to 1 if the baby is determined to be of low birth weight, and is equal to 0 if the baby is not low birth weight. and low birth weight is a cutoff of 2,500 grams or lower. The last set of questions that we want to answer are questions about this categorical outcome. And we're going to relate various predictors to this categorical outcome. So for example, we could ask the question, does a mother's smoking status impact the birth weight status? So does a mother's smoking status predict whether the baby is low birth weight or not? Or does a mother's pre-pregnancy weight impact birth weight status? The first task that we'll use to address these questions is the table analysis task. In the table analysis task, we relate a categorical predictor to our binary outcome of low birth weight or not. After we look at the table analysis task, then we'll fit an actual binary logistic regression model. The outcome in this model is our binary outcome of low birth weight, yes or no, and then we can add in predictors just like we added in the linear regression task. Let's go back to SAS On Demand for Academics, and we'll use the table analysis task and the binary logistic regression task. I've opened up SAS On Demand for Academics. I'm going to my Tasks menu, and I'll go into the Statistics menu and open up a table analysis task. Once again, I'll maximize my screen. We could perform this table analysis task to relate each one of our categorical predictors to our binary outcome of low birth weight, yes or no, but I'm just going to show one of them here. The convention is to specify the predictor in rows and the outcome in columns. So in the row, we're going to provide one of the predictors of interest, and I'm going to put history of uterine irritability here because we saw that that was a significant predictor in the last demonstration. So I'll hit OK. Then our column variable, this is going to be our low birth weight, yes or no outcome, and that's the variable low. And I'll say OK. Let's look at our Options tab. We'll leave the plots. I'm going to add some additional statistics that are shown in the tables. I'll add cell, row, and column percentages. And I'll leave the chi-square association statistics. Let's run the task. I'll look at the Code Results tab and put the output in a web browser. So here is a cross-tabulation of history of uterine irritability versus our outcome, low birth weight or not. The cell counts show the number of observations that belong to each classification of history of uterine irritability and low birth weight. And then these three different percentages refer to either cell percentages, row percentages, or column percentages. So let's look at the different percentages. These first percentages are cell percentages. So what they do is they take the cell count and divide it by the total sample size. So in this case, we take 116 and divide it by 189. So there are 61.4% of the observations in the cell for no history of uterine irritability and not low birth weight. The second percentage, this is a row percentage. And this is the percentage that we're most interested in evaluating the relationship between history of uterine irritability and low birth weight. So this is showing that among mothers that have no history of uterine irritability, it looks like 28% of those mothers have low birth weight babies. And then if we look at mothers that do have a history of uterine irritability, that percentage goes up to 50%. So 50% of mothers with a history have a low birth weight baby versus 28% of mothers without a history have a low birth weight baby. These are called row percentages because these percentages add up to 100% across each row. So for example, for this cell, we'd take 45 and divide it by the row total, which is 161. And 161 is the total number of mothers that do not have a history of uterine irritability. This last percentage is a column percentage. And these are percentages that add up to 100% over the column. So for this percentage, 89%, we'd take 116 and divide it by 130. And that leads to 89.2%. But once again, the percentages that we are most interested in are these row percentages. I'm going to rerun this output with just those row percentages. So I'll change my settings. So I've rerun the code. And let's look at the results. And once again, look at them in a web page. Here's a cleaner version of our table that shows us just the row percentages, and we can compare the percentage of babies with low birth weight in each level of history of uterine irritability. At the bottom, we have statistics that will perform a formal hypothesis test to test the association between history of uterine irritability and low birth weight category. This chi-square statistic at the top has a value of 5.4, and we compare that to the chi-square statistical probability distribution with 1 degree of freedom. We have a p-value of 0.02, which is pretty small. It's less than the criteria 0.05. And so this tells us that there is a relationship between low birth weight status and history of uterine irritability. You could go back into the options and also compute what are called odds ratios, which will compare the odds of having a low birth weight baby for each of the levels of history of uterine irritability. We have performed the table analysis task, analyzing the relationship between one of our categorical predictors and the binary outcome of low birth weight status. We could repeat this kind of analysis for each of the other categorical predictors in the data set. But I'm going to go ahead and move on, and we're going to go into a logistic regression analysis. So I'll minimize this window. I'll go to my linear models menu and select the binary logistic regression task. And I'll maximize my screen. Let's look at the different inputs for the binary logistic regression task. First, we need to specify the response variable. This will be our variable low, which is the low birth weight category. Yes or no low birth weight. The next thing we need to do is specify which level of the outcome we want to model. I'd like to model the probability of being low birth weight, and so that corresponds to low equals 1. Ultimately, when we're fitting this logistic regression model, we're not actually modeling the outcome values themselves, like we're not modeling 1 or 0. We're modeling the probability of each of these outcomes. So here we're modeling the probability that a baby is in the low birth weight category. Here we're going to specify predictors in a similar way that we specified predictors for the linear regression task. I'll add all the classification variables. This will be ethnicity. I'll hold down my control key to select each of the other categorical predictors. And I'll say OK. I'm going to again leave parameterization of effects and treatment of missing values at their defaults, like we did for the linear regression task. And then I'll add the continuous predictors. So this is age and the mother's pre-pregnancy weight. And say OK. Let's look at the Model tab. Now this is a little bit different than the tab that we saw in the linear regression task. Here it's asking us what kind of model we want to specify, and the default choice is a main effects model. So in this case, we do not have to go into that effect selection box and select the actual model effects. This will give us a main effects model without doing that. We also could choose a main effects model with all n-way interactions if we wanted to explore different interactions between the different predictors. So I'm going to leave this at the default for main effects model. I'll go into the selection tab, and once again we can apply model selection techniques here in order to choose the best set of predictors for a binary outcome. I'll select the pull-down menu here, and once again I'll choose backwards elimination. This will start with a model that has all the predictors in it, and then remove each predictor one at a time, starting with the least significant predictors first. Let's check out the rest of these tabs. I'll go to the Options tab. I think everything here is fine, and I'll go ahead and run the code. I'll go to the Code Results tab and open this output up in a web browser. Remember here that we are modeling the binary outcome variable low birth weight yes or no. The first several tables look very similar to the tables that we saw at the top of the linear regression output. Notice this note though. It tells us that the probability modeled is the probability of low equals 1. So we're modeling the probability of being low birth weight. There's some information about the backwards elimination that was performed. And here it's giving us information for each one of the steps. So it starts with step 0, and it tells us that it is entering all of the steps. Then it tells us that the effect of number of doctor's visits in the first trimester is removed. That's the variable FTV. Scrolling down the output, it then tells us that age is removed. And also, interestingly, that the history of uterine irritability is removed. We did see in that previous table analysis task that there was a significant relationship between uterine irritability and our binary outcome. It tells us that no additional effects met the criteria for the backwards elimination, and so it gives us a summary table of the variables that were removed. The final model is shown in the bottom table. Let's look at this type 3 table analysis of effects. This gives us an overall significance test describing the strength of the relationship between each of the predictors and our binary outcome. We see that the p-values for each of these tests are highly significant, indicating a significant relationship between ethnicity, smoking status, history of preterm labor, history of hypertension, and the mother's pre-pregnancy weight. And all of those have a significant relationship with our binary outcome of low birth weight, yes or no. This table shows us the parameter estimates for each one of these predictors. In this logistic regression model, the outcome is actually what is called the log odds. So odds describe the probability of the event divided by the probability of the non-event. So log odds in this case, we take the probability of being low birth weight, divide it by the probability of being not low birth weight, and then take a link function called a log. And the reason that we apply a log link to the odds is to linearize the relationship between our outcome and these predictors. And specifically, remember that the outcome that we are modeling here is the probability of being low birth weight. And so we apply a log in order to linearize the relationship between that and our predictors. Each of these parameter estimates is on the log odds scale, not on the scale of the original data. And you'll notice that the significance tests here are similar, or actually identical in most cases. So for example, for each of the variables that has 2 levels, these p-values are the same, so 0.0288, for example, or 0.0058, for example. But the p-values differ when you have a categorical predictor with more than 2 levels, such as is the case with ethnicity. The binary logistic regression task gives us a table of odds ratio estimates. This is a great summary statistic when your outcome is binary and you're wanting to characterize the probability of the event for different levels of the predictors. So let's take a look at, for example, this second one. So this is comparing the odds of being low birth weight for ethnicity level 2 versus ethnicity level 3. An odds ratio of 1.49 is telling us that mothers with ethnicity level 2 have 1.49 times the odds of having a low birth weight baby than mothers of ethnicity level 3. An odds ratio less than 1 means that certain levels have a smaller probability of having a low birth weight baby. So let's look, for example, at the odds ratio for the history of hypertension. The odds ratio here compares mothers without a history of hypertension to mothers with a history of hypertension. This tells us that the odds of having a low birth weight baby for a mother without a history of hypertension are 0.17 times the odds of having a low birth weight baby for a mother with hypertension. So in other words, the odds of having a baby of low birth weight are much lower for mothers that do not have hypertension. We also have confidence intervals on these odds ratios, and if these confidence intervals do not include 1, then this shows that we have a significant relationship between that predictor and our outcome. We have concluded our analysis in SAS On Demand for Academics. We started this demonstration by doing some basic descriptive statistics. We computed frequency tables for categorical variables. We computed descriptive statistics and histograms for continuous variables. Then we looked at basic statistical tests like a t-test or analysis of variance, relating continuous birth weight to several of our categorical predictors. And then we started trying to relate various predictors to the continuous birth weight outcome. As we did that, we started with some more descriptive analysis. So we created several plots of the continuous predictors versus the continuous birth weight variable. Then we also looked at plots of the continuous birth weight outcome versus categorical predictors. After we performed that descriptive analysis, then we fit a linear regression model. In that linear regression model, we used a backwards elimination procedure in order to come up with our best model to predict baby's birth weight. Then the last thing that we did with SAS On Demand for Academics is we transitioned over to some categorical analyses. In this case, these are analyses where our outcome is categorical. We analyzed the binary outcome variable low birth weight, yes or no. We looked at a contingency table relating a categorical predictor to our binary outcome, and then we fit a logistic regression analysis. Again, looking for the best set of predictors to predict the binary outcome, low birth weight or not. I'd like to end this demonstration with some resources for future study. The first is our SAS Educator portal, and this includes resources for faculty and educators. The SAS Educator portal includes instructional materials for data science, machine learning, statistics, and SAS programming. And this includes over 100 teaching kits that you can use to teach analytics in your classroom. The teaching kits include slides, they include the course notes both in PDF and Word format. This means that you can edit the content if you'd like, and they also include any course programs and data sets. We also give access to several industry-specific classroom activities. So these are things like homework problems, or we have what are called SAS on-the-job activities, where students answer questions analyzing a real-life data set. On the Educator portal, educators can also access free e-learning. So this is e-learning to teach statistics, machine learning, and SAS programming. There's also information about certification paths, and each of the e-learnings can be preparation for those paths. The Educator portal has information about educator workshops and training, much like the demonstration that you've listened to today, as well as discounts and promotions. Register for the SAS Educator portal at www.sas.com/teach, and you want to register with your academic email address. Our second resource is for students. This is SAS Skill Builder for Students. SAS Skill Builder provides several resources for students to learn data science, machine learning, statistics, and SAS programming. SAS Skill Builder has access to over 20 free e-learning courses on various topics, and then these e-learning courses are also grouped into 9 certification pathways, and these certification pathways include preparation materials. Faculty could assign these e-learnings to students in a course, or students could take these e-learnings independently as desired. We also have information about various career resources, such as why data analytics is a rewarding career and what it means to be a data analytics professional. Register for SAS Skill Builder for students at www.sas.com/skillbuilder, and you want to register with your academic email address. Thank you very much for your participation in this demonstration. If you have any questions, please feel free to email me at jacqueline.johnson@sas.com, or feel free to email Global Academic Programs at academic@sas.com. Thank you.